SpaceX says it plans to launch an NVIDIA AI supercomputer into orbit as soon as next year. Not a tiny chip running a navigation model, Elon Musk described the Starmind satellite as essentially an optimized Vera Rubin NVL72 computer, the kind of rack-scale system NVIDIA built for the largest AI factories on Earth. SpaceX is also making a much bigger bet. The company says future orbital data centers could use near-constant solar power, Starlink laser links, and Starship launches to escape the electrical bottlenecks slowing AI on the ground. It sounds brilliant. It also sounds slightly insane. Because space may give you sunlight, but it takes away air, repair crews, and the luxury of swapping a failed GPU on Tuesday afternoon. So today, we are asking the question behind the headline, is SpaceX about to change where AI lives or build the most expensive server rack in history? The immediate winner is NVIDIA. During SpaceX's August earnings call, Musk said the company had decided to build its AI infrastructure exclusively on NVIDIA. He called Vera Rubin the best architecture and described it as the best AI computer. That is a remarkable endorsement because SpaceX is not merely buying ordinary servers. NVIDIA's Vera Rubin NVL72 is a complete rack-scale system. It combines 72 Rubin GPUs, 36 Vera CPUs, high-speed NVLink connections, networking, storage access, power delivery, and cooling into one tightly coordinated machine. NVIDIA says the system can deliver dramatically more inference performance per watt than its previous Blackwell generation. That matters everywhere, but it matters even more in orbit, where every watt, kilogram, and square meter has to earn its trip. Musk said the first Starmind satellite would be essentially an optimized NVL72 and could begin launching in 2027. The word optimized is doing heroic work in that sentence. A terrestrial NVL72 lives in a carefully controlled data center. It expects liquid cooling, stable electricity, high bandwidth connections, technicians, replacement parts, and a building that does not shake like a rocket during launch. An orbital version must survive vibration, vacuum, radiation, thermal cycling, and years without a service call. This is not SpaceX putting a normal server rack in a metal box. If Starmind is real, it will be a new spacecraft built around AI compute, and that distinction explains why this story is larger than one satellite. The argument begins with electricity. AI companies are racing to build data centers faster than utilities can connect them. New campuses need land, substations, transmission lines, permits, cooling systems, and power plants. Even when the chips are ready, the grid may not be. SpaceX argues that orbit changes the sequence. In a dawn-dusk sun-synchronous orbit, large solar arrays can remain illuminated for most of the orbit. The company says future compute satellites could avoid many terrestrial delays involving grid interconnection, construction, and power procurement. Starship is the other half of the pitch. SpaceX's SEC filing says an orbital AI system would replace some terrestrial construction cost with satellite manufacturing and launch cost. If Starship becomes fully reusable and flies frequently, the company believes it can move enormous amounts of compute hardware into orbit. Then Starlink's laser network could connect those satellites to one another and route data back to Earth. There are also workloads that naturally belong closer to space. Earth observation satellites generate huge amounts of imagery. Processing useful information in orbit could reduce the amount of raw data that must be sent down. Autonomous spacecraft could make decisions without waiting for a ground station. Scientific instruments could filter or analyze data at the source. NVIDIA is already targeting those uses with its Space One Vera Rubin module, a smaller platform designed for the tight power and weight limits of spacecraft. That part of the market is relatively easy to understand. Put compute near the sensors. The more radical claim is that orbit could eventually host large-scale AI infrastructure serving users on Earth. And that is where the story gets difficult. You have probably heard the sentence, "Space is cold, so cooling a data center should be easy." That sentence is almost perfectly backwards. On Earth, data centers use air or liquid to carry heat away from chips. In a vacuum, there is no air. Heat can move through the spacecraft by conduction, but the only way to dump it outside is radiation. NASA's thermal control guidance is blunt. The heat generated by electronics must be conducted to radiator surfaces and emitted into space. The hotter and denser the compute, the more radiator area, coolant plumbing, pumps, heat pipes, coatings, and orientation control the spacecraft may need. SpaceX's own filing acknowledges this. It says AI compute satellites require substantially larger radiators and solar arrays than communications satellites. It describes vapor chambers, active cooling loops, radiator panels, and coatings. So yes, space provides a cold sink. But the heat does not politely leave the GPU because it can see the stars. You have to move that heat across the spacecraft, spread it over a large surface, keep the radiator pointed away from the sun and Earth, and do it without adding so much mass that the launch economics collapse. This creates a brutal loop. More compute requires more power. More power creates more heat. More heat requires more cooling hardware. More hardware increases mass. More mass requires more launch capacity, and more launch capacity increases cost. SpaceX believes Starship breaks that loop by making mass to orbit cheap enough. But until the company publishes Starmind's power, mass, radiator area, and sustained compute performance, that remains the central engineering question. The first real signal will not be a beautiful launch. It will be whether the satellite can run a meaningful AI workload continuously without throttling, overheating, or failing. Cooling is only one problem. Commercial AI accelerators are optimized for performance, not for cosmic rays. NASA explains that energetic particles can flip bits, corrupt memory, degrade electronics over time, or trigger destructive single-event effects. Space hardware often uses shielding, error correction, redundancy, watchdog systems, and radiation-hardened components. But hardened processors usually trail the cutting edge in performance. That creates another uncomfortable trade-off. The entire economic case depends on flying the newest, most efficient AI hardware. Yet the newest hardware has the least flight history. SpaceX says it will use radiation-tolerant designs and intensive testing before launch. It also says it does not expect to repair processors in space. That means failure becomes part of the fleet economics. On Earth, a bad GPU can be replaced. In orbit, a bad GPU may become a very expensive piece of debris with a solar panel. The company can use redundancy and shift workloads around failed systems. But every spare component adds mass, and every early replacement reduces the useful life of the investment. Then there is the upgrade problem. AI chips improve so quickly that a satellite launched with today's frontier hardware may look inefficient several years later. SpaceX says older systems could be moved to lower intensity workloads and eventually retired. That is sensible. It also means this is not infrastructure you launch once and admire forever. It is a constantly refreshed orbital fleet. At that point, the business begins to resemble Starlink. Except every satellite contains some of the most expensive computing hardware in the world. Even if the chips stay alive and cool, useful AI needs data. A large model is not one processor answering questions alone. Training and advanced inference require GPS, memory, storage, and networking to exchange enormous amounts of information with very low delay. On Earth, NVIDIA's advantage is not just the GPU. It is the system around the GPU, NVLink inside racks, high-speed networking between racks, software, and a mature ecosystem. SpaceX wants to extend that system with intersatellite laser links. Its filing points to more than 23,000 lasers already operating across Starlink as evidence that it can build a space-based mesh. That is a real advantage. It is not the same as proving that a constellation can behave like a tightly coupled AI factory. Some workloads are forgiving. A satellite can process imagery locally, compress results, or run inference without constant communication with thousands of other accelerators. Frontier model training is less forgiving. If GPS spend too much time waiting for data across a network, expensive compute sits idle. This may be why the first useful orbital market is not replace every data center on Earth. It may be narrower, inference close to space-based sensors, autonomous operations, specialized scientific processing, and services where global coverage matters more than absolute lowest latency. That would still be a meaningful business, but it would be very different from the cinematic image of a giant cloud computing empire floating above the planet. The smartest version of SpaceX's strategy may begin with workloads that make sense in orbit, prove the platform, and expand only when the economics become undeniable. Now we can ask the only question investors and customers ultimately care about: what does a useful token cost? SpaceX argues that near-constant solar energy, automated satellites, its laser network, high-volume manufacturing, and reusable launch can eventually create a lower-cost structure than terrestrial data centers. The filing describes early satellites targeting roughly 100 kilowatts of compute power per metric ton. It also presents a long-term ambition of deploying up to 100 gigawatts of orbital compute capacity per year. That number is not a forecast. It is a vision requiring thousands of launches annually and approximately 1 million metric tons delivered to orbit each year under SpaceX's assumptions. The company also says a much smaller deployment rate could still produce an attractive business. That is the more credible near-term test. The economics must include the processor, satellite structure, solar arrays, radiators, launch, insurance, networking, failed hardware, replacement launches, ground stations, and the fact that an orbital GPU cannot be repaired. Terrestrial data centers have their own expensive problems, but they are not standing still. Nuclear projects, natural gas generation, improved grid equipment, liquid cooling, better chips, and flexible power management could reduce the advantage SpaceX expects from orbit. SpaceX itself acknowledges this risk. If terrestrial power becomes cheaper or easier to access, the case for orbital AI weakens. That is the key reversal in this story. SpaceX is not competing only against other rocket companies. It is competing against every improvement made by utilities, chip designers, data center builders, cooling companies, and energy developers on Earth. Orbit does not need to be possible. It needs to be cheaper or uniquely useful. NVIDIA wins first. Whether SpaceX launches one Starmind test or thousands of compute satellites, Vera Rubin becomes the reference architecture for one of the boldest infrastructure experiments in technology. NVIDIA also gains something more valuable than a purchase order, a new market narrative. AI computing is no longer limited to data centers, factories, cars, robots, and personal devices. It can be sold as infrastructure that extends into orbit. SpaceX wins only if it proves the system. Watch 5 signals. First, does a Starmind payload actually launch in 2027? Second, does SpaceX publish sustained performance, power, and thermal data rather than a short demonstration? Third, what workloads run first? Local inference and sensor processing, or tightly connected large model computing? Fourth, how much useful compute survives after radiation, heat, and component failures? And fifth, does Starship reach the launch cost and cadence required to replace and expand the fleet? If those answers are strong, orbital AI stops being a science fiction pitch and becomes a new layer of global infrastructure. If they are weak, Starmind may still be an impressive experiment, but the largest AI factories will remain exactly where technicians can reach them. So, is SpaceX about to change where AI lives? Not yet. But the company has moved the idea from a distant presentation slide to a named satellite, a selected NVIDIA architecture, and a public launch target. That is enough to take seriously, and not enough to take on faith. Would you trust the world's most expensive AI hardware in orbit, or would you keep it on Earth until the economics are proven? Tell us which milestone would convince you. We will respond to as many questions as possible, and if you want deeply researched stories about AI, robotics, space, semiconductors, energy, and the businesses shaping the future, subscribe to Future Signal. Future Signal.